Zhu and Chu are practicing their 100-meter sprints by running 6 races against each other. Zhu wins the first race, and after that, the probability that one of them wins a race is 2/3 if they won the previous race, but only 1/3 if they lost the previous race. The probability that Zhu will win exactly 5 of the 6 races is m over n, where m and n are relatively prime. Find m plus n. Okay. So of course we don't have to worry about the pair really. We're only going to focus on Zhu. How do I want to set this up? I certainly understand the dynamics of the problem. But what I don't want, so there are 5 races we need to account for. There's 6 races in total, but we know that there's a win in the first one. So there's only 5 more we need to account for. We could write out every possible sequence. That's 32 different sequences. I'm not sure if I really want to do that. I'd rather simplify the problem in some way. Like, we can think of this even as like a, think of it as a binomial tree. One, two, three, four. And then we'd have one more set of branches. So because the first one was a win, the probability we win the next one is 2/3, 1/3 of losing. And then if we won this one, the probability of winning here is 2/3, 1/3 of losing. Here the probability of winning is 1/3, 2/3, 2/3, 1/3, 1/3, 2/3. This is 2 over 3, 1 over 3, 1 over 3, 2 over 3. So you can see there is like a pattern here. The way that these probabilities are arranged is the same as the way these probabilities are arranged is the same as these probabilities are arranged. So each sort of each set of things in a tree like this is the same. And so I think there's probably going to be like maybe there's like a recursion that we can write down. So if P is the probability of a win after a win, and Q is the probability of a win after a loss, so these are 2/3 and 1/3. What if we solve a very simplified version of the problem? Like, let's say we win the first race, and then there are 2 more races after that. So the probability of 2 wins will be P squared. The probability of, let's write this as WW. The probability of win-loss is P times 1 minus P. The probability of lose-win is 1 minus P times Q. And the probability of lose-lose is Q times 1 minus Q. No. 1 minus P times 1 minus Q. Right? Probability we win twice in a row is P. The probability of one win is P, and then the next win is P. The probability of the first win is P, and then the probability of a loss is 1 minus P. The probability of a loss is 1 minus P. Given that we've lost, now the probability of a win is Q. So what's the pattern here exactly? This is kind of a weird, it doesn't look like a simple binomial thing expanded. And I don't really want to brute force this and go into 3. Why don't I'll do it for 3, a sequence of 3. Okay, so this is P cubed. This is P squared times 1 minus P. This is P times 1 minus P times Q. P, 1 minus P, 1 minus Q. This is 1 minus P, QP, 1 minus P. I think I can see how we'll do this, but I'm just going to keep going. I'm going to keep going here. I'll fill this out and then I'll explain what my intuition is. Okay, so probability of loss 1 minus P, and then Q, and then 1 minus P. LLW, 1 minus P, 1 minus Q, and Q. LLL, 1 minus P, 1 minus Q, 1 minus Q. Okay, so here's my intuition. I'm not going to focus on these numbers very much. I just wanted to finish making this table. But here's my intuition. We have 5 races left. We need exactly one of them to be a loss. So here are the 5 sets of possible orderings. These are the 5 sets of, we start with a win. There's a win at the beginning of all this, but we don't really care about that because it said that we win the first race. We have 5 races left. We need to win exactly 4 of them, and we want the probability of each of these. Now we can just use, I'll just write out what the correct answer is, right? The probability that we win the first 4 is p to the 4, and then the probability we lose that last one is 1 minus p. Here we have p times p times p times 1 minus p times q. Here we have p squared, 1 minus p, q, p. Here we have p. Oh, interesting. These ones are all going to be the same. P times 1 minus p times q times p squared, 1 minus p, q, p cubed. Okay, so the answer is p to the 4, 1 minus p plus 4 p cubed 1 minus p times q. Interesting. I mean, this is starting to look like, these look like binomial coefficients, sort of. Wait, not exactly. I mean, they do. 1 and 4 are binomial coefficients, but like what... Anyway, let's just compute this. So p is 2 over 3. So we have 2 over 3 to the 4 times 1 over 3 plus 4 times 2 over 3 cubed times 1 over 3 times 1 over 3. 16 over 3 to the 4, 3 to the 5 actually, plus 4 times 8 over 3 to the 5, 16 plus 32 over 3 to the 5, 48 over 3 to the 5. 48 is 12 times 4 over 3 to the 5. So 4 times 4 over 3 to the 4. So this is 16 over 81. Those are relatively prime. So 16 plus 81 is equal to 97. Yeah. So this clicked for me. The fact that this is what I was going to do clicked for me as soon as I started writing these out. I'm realizing, like, I'm writing out all of the possible outcomes after 3 races. But given that we only want the probability of winning exactly 5 of the 6 races, obviously the strings that we look for are the ones that have exactly 1 L. So it's significantly fewer than all of them. And it's pretty easy to write out once you're given the sequence for any one single sequence. It's pretty easy to write out the probability of that sequence happening. And it's a pretty small number of sequences in total. There's something, I don't really know. There's definitely something about a way of writing this as a binomial expansion thing or something like that. But when you have events that are not independent from one another, things are a little bit, can be a little strange. But anyway, yeah, this is a cool problem. I'll let you know if I find a mistake somewhere. Thanks for watching.